Starting into this morning's presentations, our first speaker is Joe Blaschka from Washington State. Joe is a registered engineer in 8 states and the principal and founder of AdCom Engineering. Prior to starting AdCom in 1979, he worked for Motorola and a small telephone equipment manufacturer. Joe's been engineering and designing simulcast systems since the early 70s. AdCom Engineering has worked on over 500 communications projects ranging from low-band paging systems to 100 megahertz trunk systems. Joe has freely shared his expertise with us since the first forum over 15 years ago. Every few years, I ask Joe to give us a refresher on the basics. Simulcast is primarily attention to detail. And given the fact that some of us have a number of years between projects, it's always good to get a refresher as to what to pay attention to try and make your life easiest. Please welcome back, Joe. Please don't step off the side.
Thank you, Ed. Well, he said I freely share it, so I guess you get what you pay for, right? Yeah, I've been doing simulcast for a long time, and we used to have a fairly detailed simulcast basics presentation. That was back, when you had to wait so long for the tubes to warm up, and all the rest of you out there obviously are old enough to know what tubes still are, other than the things that connect the internet. But so the simulcast basics we'll talk about today is at a pretty high level. But we're going to talk a little bit more about staging, because I get calls from people all the time. They're trying to get their simulcast system aligned, and one of the things that happens is I'll say, well, it didn't work in staging, and I'll say, well, what do you mean by staging? So we'll try to get through that. So first of all, why simulcast? Well, some of you have already done simulcast systems, but for those of you that are thinking about it, one of the things that we see, and we still see it as a very viable technology, in fact, we're going to see it used more, is because it's a spectrally efficient technology. I don't know about you guys, but every time we do a project, one of the biggest challenges is finding frequencies, right? And if somebody wants to put, county-wide coverage, and you're going to want to put 10 or 15 repeaters running, you might need 20 or 30 frequencies, or 35 frequencies, or whatever it is. I don't know about where you guys are, but even in the rural areas in Washington, Oregon, and those places, frequencies are going to be hard to get, especially at VHF. UHF, maybe you can still find a few, but and 800 in a lot of places is already used up. So it's really a spectrally efficient technology. It's not cheap, less expensive than it used to be, but it's spectrally efficient. And many rural areas, of course, that are now becoming more populated, and the areas surrounding them are becoming more populated. It's even more difficult to find channels. And one of the other advantages of simulcast is it's almost always coupled, or it is always coupled with receiver loading, so you also get a pretty significant increase in talk in as well. And modern technology really reduces the maintenance requirements. I have people ask me, well, I don't want to do simulcast, but I'm kind of scared of it, or it seems like it's really complicated. And it does take attention to detail. But the reality of it is with modern technology out there today, there's really no reason why most people shouldn't be able to successfully implement simulcast. So let's talk about a couple of basics. Frequency stability. I don't think anybody would even consider doing simulcast anymore without using GPS disciplined oscillators. It's just not really an issue anymore for frequency stability. There are a couple of issues potentially with some radio manufacturers that, and how well their radios might lock to the GPS oscillator. But for the most part, stay with kind of the mainline stuff. You're not going to have a problem with that. I do get questions sometimes about whether to use frequency offset or not. Our recommendation is always not. We don't see any reason, and I know there's lots of arguments, kind of like the difference between hyperberia drink, right? It doesn't really make any difference in reality, but our experience is that with G-blend oscillators and all that, there's really no reason to do offsets, and they generally create more problems than not. So our recommendation is to just lock it down and have everything the same. Audio adjustments. This is where most people sort of get messed up, not just in the implementation, but also in the design. The phase and timing for audio or analog systems anyway is about 80 microseconds. In some cases, you might be able to go a little more than that. If you're doing paging, especially high-frequency paging like plectrons. If anybody's still using plectrons around with, well, not using receivers, they've been long gone, but they're still using plectron tones. A lot of those tones were up near 2,000 hertz, maybe higher. And so in that case, you have to think about the 30 degrees of phase difference. So the 80 microseconds number is kind of a number that you would use if you're referencing using 1,000 hertz as your reference. If you go to 2,000 hertz, though, that number goes in half. So if you're doing, fire tone out paging and you're using plectron tones, my first recommendation would be change your toning scheme. Go to quick call to, go to lower frequency pages. You won't regret it. I know it's a big pain to go out and change everybody's pagers and all the rest of that, but most of the people now are going to have programmable pagers, so they have the labor cost. But if your phase differences now are down to about, for timing, 40 microseconds, now you're talking about something that's a lot more difficult to program. Modulation recovery from all your sites needs to be about 0.2 of a dB or better. If you're using a Simpson 260 on the AC scale to set audio levels, that's probably not going to work too well. So you need to have some decent test equipment to do that, and you also really need a test receiver. I get calls from people and I'll say, well, okay, so look at your scope up to the test receiver, and they'll say, test receiver. I'm trying to use my service monitor. Well, in a lot of cases, the service monitor doesn't work very well because the front end's too broad and the sensitivity is not good enough. So our recommendation is you should always use an over-the-air test receiver at a place that can hear all the sites for setting the levels and making sure the levels are all correct. Of course, that's getting to be a little bit harder today because it's harder to find a test receiver that actually has an analog output, because they're all speech processed. So hang on to those old Master 2 receivers and micro receivers, and you can continue to use them for test receivers, or Spectras, or older GE or Paris, or whatever they were during that time, radio. Audio speech processing can make a big difference, especially nowadays with narrow banding. So we've had really good success with using a compressor type amplifier, the low level audio really helps on the narrow band. There's a couple of those around. And we also recommend using the common audio source for both voice and CTCSS. It makes the adjustments a lot easier. It also, unfortunately, sort of limits the choice of equipment. So you have to use a base station that has basically flat audio so that you can put the audio and the CTCSS tone in through the same input. And you have to buy audio cards for your channel banks if you're using channel banks that go down to 5 hertz or so you can do that. But from a maintenance standpoint, it is a lot easier to be able to adjust all of your levels at one location instead of having to make adjustments at all of the remote locations. And the other thing is, don't guess at the adjustments. Simulcast is not something that you can set levels by 1, 2, 3, 4, the old days. It doesn't work with Simulcast. Even for us old guys that listen to radios for a long time, it doesn't work with Simulcast. The other thing is you want to control your RF through the use of antenna patterns, and particularly at VHF. So the higher you go in frequency, really Simulcast is easier to do. Simulcast at 800 is actually pretty easy to do. You have a lot less problems. You don't have the long range that you do on VHF, for example. But overlap on VHF can really be a problem. I mean, it's pretty easy to have VHF show up 20, 30 miles away where you don't expect it. So you really need to do some work with antenna patterns. And we've been really successful in using antennas that have 10 to 12 degrees of down tilt to keep the RF where you want it. You don't want the RF at the horizon. Well, maybe the old days, right? On top, shoot that RF as far away as you can. With Simulcast, you don't want that. You want the RF to be where you want it to be. And I've had people say I have a 3-degree down tilt. Well, if you actually look at the antenna pattern on VHF, 3-degree down tilt doesn't really buy you anything. You've got to be in the 10 to 12 degree down tilt range for most 5, 6 dB antennas. And I know there's a lot of old guys been around a long time say, well, I don't think that'll ever work. And we've even had some of those in our own company, and they've become converts at that. It really does work. You can use even relatively high sites if you put down tilt on your antennas. And they are expensive, no doubt about that. and there's some long lead times with it, but it really does work. And you got to remember that by overlap area, we're talking areas that have signals within 15 to 20 dB of each other for narrowband. That's a huge area if you don't control your antenna patterns. I mean, we worked on projects, we call from somebody, and 40 miles away, their highway patrol goes up on an overpass, and now when they're on the freeway, it's fine. When they're on the overpass, they're now looking at a site that's 40 or 50 miles away, and on VHF, the signal level comes up enough that they have that blanking, that simulcast overlap distortion on the overpass, but they don't have it on the freeway. Just that little bit of difference in elevation, will be a problem. And those problems are pretty much all solved by putting a lot of downslope on your antennas. So let's talk a little bit about wideband versus narrowband. The only real reason this, obviously everybody's pretty much converted, hopefully, from wideband to narrowband. But it does show, if you look at the right button here, the real difference here is if you look at the black areas, these are the areas that have simulcast overlap distortion. And so here was a wideband example, and here was what happened with just the conversion to narrowband. So you can see that it's quite a bit worse. So in a lot of versions, just like people found out many times when they converted their non-simulcast system to narrowband, it didn't work as well as it did before. And the same problem exists if you had simulcast into the conversion. Now the good news though is if you're doing P25 and you currently have a phase 1 system and you want to talk about going to a phase 2 system, as you can see here, the phase 1 system, here in the black again is the simulcast overlap areas. If you look at the simulcast overlap areas of phase 2, you see that they're less. So phase 2, contrary to what a lot of people thought originally, is actually better simulcast than phase 1. So how about building a system? Because this is usually what I get involved in. Somebody calls up after they've tried to deploy a system and can't make it work. So don't build the system in the field. Just, if I could repeat anything 20 times, it would be that. It's going to take many trips out to the site. You're going to waste time, and all you're going to do is help the gas companies, right? The gas stations. If you've got sites that are 20 or 30 miles apart and you're driving back and forth, checking wiring, doing this, doing that, every time, you've got, it depends on traffic like it is in Seattle, that 20 miles will take you 2 hours to drive. So, build it in the shop. Equipment and parts are across the room. Testing the level setting is a walk and not a drive, and time saved is many dollars earned. So what does staging mean? So this is not staging, right? Putting things together with clip cords and wires hanging everywhere, that's not staging. Actually, some of these were actual installations, like that one up there with the old Nicor thing. But basically, that's not staging. I've seen people, just set their equipment on the workbench and try to make it work, and that's not staging. Because once you take it all apart, you got to put it all back together again in the field, right? And now you got all the potential for all the wiring problems and everything else. So here's some pictures of a really big project that we did. This was 11 sites, 7 or 8 channels, and all simulcast. And this is how we would stage a system. So you can see we've got the wiring's already done. You've got punch down blocks for all the cross connects. They're already wired. All this is pre-wired. We've got a lot of 960 links. So the links are all assembled. The equipment's all put together in one spot. All wiring is done, inter-rack wiring is done with cables, so you can just plug the cables together. And the only thing you have left to do is cross connects at places where you're cross connecting to equipment that you're not putting together already in the field. So when you get out to the field, in theory, assuming you don't drop one of these on the way up to the site, everything's working. You knew at one point all the levels have been set, all of the links are working, everything was set and it works, right? All the transmitter outputs were checked, receiver sensitivity was checked, everything was checked. So when you get to the site, if something doesn't work, you at least know one time it was working, right? Because sometimes you get, a system, you look at it and you go, well, is this ever working? Because you look at it and go, this doesn't look like it should ever work. And you find out, well, nobody ever tested it. So what we find a lot of times, there's a lot of pushback because people don't like to do staging, right? They like to get the stuff out of the site, right? The customer's happy, they see the equipment out of the sites, antennas going on the tower, they feel like work's going on. But a lot of that is just how you explain it to the customer. They also, a lot of times, like to see the stuff in your shop, right? If you can bring them in and show it, hey, here's everything working, you can do test calls, stuff with all the equipment in your shop. That can actually sometimes even be a payment point. If it's done correctly, then virtually everything, all your wiring errors, not that any of you out there would make wiring errors, but what we do every once in a while, have a error that gets rolled, or somebody colorblind when they're looking at color code. So all of that stuff you take care of in your shop, right? It's a lot easier to do, and you do it with everything, right? Get your RF links working. Make sure that the transmitter and receivers, like on those 960 links, make sure they're talking to each other. You don't want to find you got a bad receiver when you're up at the site. It's a lot easier to find it in the shop. And this process we found can take days or weeks off of system deployment, but it takes planning. And my last comment there is no whining about how much work it is, because too many people seem to think that running back and forth to radio sites isn't work, but trying to build this stuff in your shop is work, but it's really important to do the staging. And everybody wants a successful project. You guys want it, we want it, the customer wants it, vendors want it, the equipment vendors want it. And so what does success equals a happy customer? They can see their system working. It's going to be more profitable for you guys to do that. It's going to be less maintenance and a smaller number of warranty calls if you get them all working and properly installed in your shop before you take it out. So you really got to resist the temptation to cut corners on anything to do with simulcast, because it'll bite you in the long run for sure. Unless, of course, you're charging time and materials for maintenance, and then who cares how much maintenance you have to do, right? Because that's a profit center. But if you're doing it on a contract basis or under warranty, then you want to make sure your maintenance costs are as low as possible. So that's it.
Thank you, Joe. Thank you, Joe. Our next speakers are Bruce Resto and Don Basilis of Bartronics in Chesterton, Indiana. Bruce started Bartronics 35 years ago after graduating from Purdue University and Valparaiso Technical Institute with a BSED. He learned practical electronics from Valparaiso Technical Institute. Don has been in the radio industry for 25 years, since he was 17. The day after graduating high school, he started training himself in the School of Hard Knocks. Don owned his own radio shop before joining Bruce. Bruce and Don implemented a very cost-effective RF link simulcast, proving a simulcast doesn't have to break the bank by significant customer advantages. Thank you, guys.
Good morning. As was stated, we ended up and had an opportunity to do a simulcast system after attending a session such as this. We were asked to find a solution to overcome extremely poor police communications inside of a local school. Now, with everything that's going on in the schools, you know how important that is. We thought it was a perfect opportunity to introduce ourselves to a simulcast system as well as the municipality. The system had to be seamless so that any police personnel on site would not have to worry about changing channels on radios or carrying a second radio possibly in the event, of emergency. A simulcast communication system was installed to fix school resource officer communications. The main problem was that the high school resource officer could not communicate with the police dispatch, even though the dispatch repeater was actually less than 3 miles away.
two-site system, simple. We did it with UHF radio links that linked our audio. The hardware, was the very reliable Motorola MTR 2000s. We had an existing Raytheon SMP 12 voting system. We were able to take advantage of that, which worked out great. Of course, the Spectracom Secure Sync for our GPS and external frequency reference, the input to the MTRs. The Spectracom CTCSS tone filter. And for our radio links, we used low-cost UHF ICOM mobile radios. Now, we've used ICOM successfully as voting receivers, junction with Motorola receivers, and have been very, very successful. They work great, we know they're reliable, so that's what we use. The transmitter locations both had duplicate setups. We used the exact same thing at both sites. The short distance from the main site wasn't a huge concern for timing, so we didn't have any delay issues to worry about. But one fortunate thing for us, the one receiver from the SMP 12 was located at the high school, so we were obviously going to take advantage of that. We extended the transmitter operation for our second VHF site to inside of the high school. So our UHF link linked our transmit audio from the SMP 12 at the police station to our UHF link, which in turn sent that to the MTR 2000. The simulcast controller and the second MTR transmitter were placed on the third high school. It was in a mechanical room that was easy access to the roof to get our antennas out to the roof. And the transmitter output from the MTR, the VHF output, was routed to the second story of our three-story school, so that we had basically a central location for our transmit antenna. We took the MTR down to 25 watts, which was more than sufficient to cover all the floors of the school and all the areas that we needed. We routed that, hid it inside the drop ceiling of the school. There's nothing penetrating the school at all. They can't even tell it's there. So it covered the school's 3 stories, no problem.
To help the school resource officer get into the voting receiver system of this portable radio, we enhanced the existing school MTR 2000 voting receiver by adding special receiver antenna networks in that school. We added antennas on all 3 floors, added a high gain type amplifier for the receive section, tied the existing school roof antenna to the motor as well through commercial splitters, and we fed the signal all back to the existing SNB 12 at the police station through the existing MTR 2000 repeater. So that made the receive side in the school fairly easy, except for running cables and antennas and things like that on all 3 floors. The existing phone lines and everything else made it all just work extremely flawlessly.
Here comes the plug for Ed and Simulcast Solutions. The MTR repeaters were wired for external audio and CTCSS inputs, instructions from Simulcast Solutions, no problem, easy to follow. And to the point I think was made earlier, we made sure the audio levels and the CTCSS levels were as close to equal as we can get them voltage-wise per Ed's instructions. And it worked great. So we actually had the opportunity to test this whole system staged in our shop. We tested it, had it all set up, and an advantage to us is this was an existing conventional repeater system, so we were able to hear the traffic in our shop. So we actually repeated through our simulcast system at the shop the actual audio we were going to use for the system. So it worked out great. When we tested it, we wanted to listen to make sure the audio was good. So when we did set up the system at the police station to run, before we switched them over, ran it on a second VHF channel. We had the opportunity to hook to their tower on an unused antenna. So we monitored the actual output on a separate frequency so we can actually hear both channels simultaneously. we wanted to compare the audio, the way it sounded. The reason for that is because, as you know, the existing sound that the police officers are used to in the field is going to be what they want to hear. If anything changes, there's a pitch change, the dispatcher doesn't sound the same. The radio guys are the first ones they're going to complain to. So we listened, days. There's a pretty busy smaller police department, so it was pretty easy. So once we compared that, listened to the quality, we were happy with what we done. So we wanted to be sure, and when it was done, they did not detect any audio changes. So the whole thing was setting it up at the shop, staging it, and our opportunity to listen before we switched it over was probably paramount.
The customer was satisfied with this Simulcast system. We were able to implement it and do so with a total system downtime of 20 minutes. Now you think about that. We put a Simulcast system in, even though it was a relatively easy system. We had them off the air really less than 20 minutes. And we flipped the switch basically because, as Don mentioned, we had everything set up. We were listening to the channel as it was being simulcast on another frequency. So basically it was reprogramming an NTR 2000 and doing some other quick hookups. And then the system was in place within 20 minutes. The simulcast system came online. It was business as usual. And most of the officers and people using the system had absolutely no indication the system was changed, except for the school resource officer, and he knew that by the added coverage and reliability of the school system itself. So this satisfactorily allowed him to get into the repeater system and actually be able to hear the police dispatch communications, where normally he couldn't hear at all.
Okay, as I mentioned before, we wanted the audio to be mirror-like, so when it was switched over, we didn't have any complaints. There was an issue that we had with the transmit audio from our SMB12 transmitter output to our ICOM radio, and it probably may have been the same for other radios as well. So we ended up using a CPI termination panel as our audio processor. So we took our line out from the SMB12 into the CPI and used that microphone output to drive the audio to our UHF radio link. So the matching between that, we made a few modifications to the CPI to give us more audio control. So that anybody who's tuned an MCR 2000 audio levels on anything, it's hard. There's levels here, put this and put there, it changes. So we wanted external control of that, and the CPI allowed us to do that. So the input to the UHF radio link made all the difference in the way our transit audio sounded going to the two receivers.
The thing with this project was that it was actually easier to do than we expected. We went into it sort of semi-horrified that we've never done one before, but when it was actually done and we kind of reflected back on it, it seemed like it was easier than we certainly expected. Some of the things to the success of the project was that we checked and double-checked everything we did. And rechecked it again once it was all checked, right? Exactly. I mean, it was just, as was mentioned, staging in your shop, setting the system up, being sure that the system is what you expect it to be, is the most important thing that could be on the whole project. We're both extremely anal about how systems sound and the quality of the voice, etc. If it didn't meet our expectations, why we knew it wouldn't meet the police departments. So, being able to take the time, set it up, test it, put it in place, and test it again, made us a believer that it was going to be working fine. It's far from total plug and play. We had to reinvent the wheel a few different places, like Don mentioned, with the CPI panel and whatnot, but that worked great. But with thought and testing, it worked very well. The next Simulcast project we do will go a lot easier with the knowledge that we gained from this first system. We know that we know what we will need to do and why, and this should limit the amount of time and experimentation for the next project. Kind of an interesting side note is that we were able to get Communications High School as planned and do it with the Simulcast system and still beat competitors by $10,000 to $15,000 on the system price compared to using PDAs as a method to get signals in and out of the system. And believe it or not, we made a lot of money on this thing doing it too, even though we saved them $10,000 or $15,000.
Thank you.
Yep, thank you, Ed.
Thank you.
So, this project group will be extremely cost-effective for us in the school.
I just wanted to thank Ed for the money-making part of it. The interesting thing here is that we did this for the police department for their communications inside the school. And since the project has started, we also had inquiries from the local fire department on how they can improve their communications, not only in just the school, but other maintenance, factory facilities, things like that. And now the city that we did this in, they're actually talking about putting a law on the books for any new construction to have the built-in capability of seamless communications once an officer or first responder enters that facility. So they're actually looking to write that into a law. And just two quick things. Obviously, we didn't have a huge problem with overlap because of the shielding of the school. Instead of driving around, we had to walk around. So we walked around the whole school inside and out. We had no overlap issues. And one thing we did change as the conversation of this project progressed. The UHF Yaki at the police department, we changed to an Omni just before the project was completed, because there was already talk of the police department extending that to other sites where they have portable issues. So it's already progressed into more talks about expanding that system. We've done already. So thank you very much. Anything else?
No, it's just that the way we did that with, like Don talked about, will allow us to add other sites, and all we've got to do is just tag onto that UHF signal, and then add another repeat site wherever they would want it. So basically 60–70% of all the infrastructure is there. We just have to tag onto it to expand it.
All right. Thank you very much.
Thank you, guys. Thank you, Bruce and Don. Coverage reduced by narrowbanding continues to cause some customers to add additional sites to improve talk-in and talk-out. A little over a year ago, Raycom installed an 8-site simulcast system in Wisconsin, which used master retransmitters connected by an IP backbone, which used gauged air, net express multiplexers, and audio control. The system was implemented by Tim Broderick. Tim started with Raycom back in 1985 as an installer after working in the dairy industry. He says he's come full circle. He left the dairy industry for more regular hours. And now, like most of us after all these years, the irregular hours have managed to find him again. Tim agreed to share his simulcast experience as the project keeps expanding, in a good way. Let's welcome Tim.
Okay, Raycom Corporation was asked by a local Harris dealer in Wisconsin to team up with them and help bid on a narrow banding simulcast project for the city and county of Eau Claire, Wisconsin. We immediately contacted Ed at Simulcast Solutions and told him that IP would be our mode of connectivity. Ed put together a package of pieces that we would need, including the Spectrocom secure sync clocks, gates air net express fluxes, convex audio and push-to-talk distribution panel, JPS voters, and narrowband optimizers. The consultants in charge of this project asked for an analog simulcast system, so we chose to bid Harris Master 3 stations to do the work. The existing layout consisted of about 17 conventional repeaters in use between the city and agencies. The city had a primary transmit site, and the county had a different primary transmit site. The two entities shared some common tower sites where voting receivers were located. The city used about 6 sites, and the county used all 12 of the sites. The backhauls to the voters were a mixture of RF, phone lines, analog microwaves. It was decided to simulcast 3 channels for the county, transmitting from 8 of the 12 locations. Eau Claire had fiber buried everywhere throughout the county as part of a BTOP project. Before we began staging, Eau Claire was making sure fiber connections were waiting for us in each tower site. We staged the equipment in a warehouse. Gates Air had built us up a system that would accommodate the 3 channels of simulcast at 8 sites. Along with the connections, 4 receive-only sites to bring them back to the voters. Just before we were ready to move it out and deploy it, the county had decided that they were under budget enough to put in another simulcast channel. We ordered more Master 3 transmitters. We also decided at that time not to just build for 4 simulcast channels at 8 sites, but prepare for 2 more channels just in case. During the build-out testing of the simulcast system, the city of Eau Claire was seeing the benefits of simulcast. They decided to simulcast 3 of their channels at 2 locations, with options to expand that down the road. A new head end was created at their primary transmit site. More Master 3s and Gates Air Muxes were ordered. Currently, the city is still simulcasting 3 channels from 2 sites. It has 4 channels of simulcast from 8 sites, and the Township Fire has 1 channel simulcast from 4 sites. Besides controlling our simulcast, our Gates Air Muxes connect about 125 auxiliary receivers to 17 voters for both the simulcast and non-simulcast channels at 2 different head ends. They also connect our consoles directly to the JPS voters. And we recently received word that they want to add on to their system. Okay, Ed.
You need a simulcast clicker.
I need a clicker. There we go. Yes, the initial system was 8 transmits, receives 3 channels per site, added on before we could put it out, and expanded all the time we were out there and implementing. This was a map of our muxes, basically tied over fiber links. They had 2 fiber rings, and we had a microwave shot down to Osseo. When we added the city's simulcast equipment, we had to create another head end. The purple boxes were put in to establish that simulcast system for the city. Equipment we used, Master 3s, Gates Air Express, Spectracom, Fox, and Raytheon rotors. This was our staging area. Someone mentioned like an airport hangar. It was a warehouse. We lined the racks up according to what site they were going to. So each row was a site, and we began putting our equipment together there. This is a picture from the head end on the 4 channels for the county. On the back side, we used, basically didn't use punch blocks, we used Cat5 cable to connect with using RJ45 jacks. We used banjo, 8-conductor banjos for testing. It was easy to unplug, plug in. This was our city's head end. Our connection diagrams, you had to kind of get it straight in your head. It's nice to draw it out. Have something to reference. So we had our GPS, our narrowband optimizer, the convex units that created our channel baritone, and the unit that distributed our audio. And then we ran it down to patch panel. This is one of our county's sites, simulcast sites. Some connections that we made to Master 3 so that it made it easy to take apart, move out, put back together again. And connections to, the city used the 1118 boxes for their channel guard, so we had some drawings on how that connected. I guess that's it. Thank you.
This next session is a very brief what's new and what's coming for new products in the area. Spectracom Secure Sync now has 12.8 megahertz outputs, which can be used with legacy Tate T800 base stations. And it also supports VHF high offsets for those who want to try it. Again, as Joe talked about, with offsets, the pro is it sometimes eliminates nulls. The downside is it creates a periodic chopping sound, and most people that try offsets find that they'd rather have these small nulls than to have the chopping all the time through the overlap. If they're available to someone, because I've had a few requests for it, and that's now a module you get to put the back of the secure sync.
Yeah.
Yes?
Quick question on those offsets. If I recall correctly, the blade that goes in there is like 4 BNCs on it or something like that to do the offset. Is that correct?
The module has 4 BNCs, that is correct.
Is each BNC capable of its own offset, or are all 4 tied together, so they all have the same offset?
Okay. On that particular module, each of the 4 BNC outputs can have a separate offset. I will tell you that an offset is in 1.5 hertz steps. So VHF high, UHF offsets have by the way, the offsets are actually offsetting at 10 megahertz, which then gets multiplied up to the VHF. So the offset corresponds to give you 1.5 hertz of VHF. UHF offsets, when they were used, were typically a 0.5 hertz, which is a multiplication of 36 instead of 12. These offsets would be really large at UHF, so we're not able to easily do UHF offsets in this module. That's why I talk about VHF steps. But yes, 4 individual ones. So at a particular site, you could have one that's plus 3 hertz, one that was minus 6 hertz, or what combination.
Great design, thank you.
Okay, thank you, Bob. The Raytheon SNV12 added a new level of the browser interface, which is essentially a dispatcher or user level. The dispatcher or user can force vote or force disable sites, but is not allowed to play with the edge or any of the system parameters of the voter. That would remain an administrator function in the SNV12 browser interface. That is a software download free from Raytheon JPS. It may be what you have already. That depends how old the voter is. As long as you have CPM3, which has the IP port, so it has an IP port on the front, It's a download. You'll need to contact Benny Hillman at Raytheon because Benny has to send you the software due to export restrictions that Raytheon is under that a lot of commercial enterprises aren't, but they are. Gates Air Net Express has added a new automatic switchover feature such that if a shelf at a head end or remote site fails or is no longer present, another site would automatically take over within 3 seconds and keep going just like the site that's potentially. So that is a multiplexer enhancement for people that have redundant head ends, redundant dispatch centers that want to have that automatic switchover happen without any human intervention happen quickly. In the last few years, SpectraCom SecureSync has added a 5 megapulse per second 1 TPS output, which is used for interfacing to MLC 8000 Motorola motors and to some of the GTR 8000 products. There's a reverted selector card in the SecureSync, which lets you inexpensively take and have a redundant input for 1 TPS, 5 meg or 10 meg. It'll switch over. It sits in a SecureSync chassis as a host, but if power is removed, the relay automatically fails over to the backup, so you always get connectivity. So if you put 2 SecureSyncs on 2 different breakers and 2 different power supplies, that would always be the source coming through relatively inexpensively if you need just a single output of 1 TPS, 10 meg or 5 meg. There's also a new user interface for the SpectraCom SecureSync, which gives a whole lot more logs and information, as well as being easier to maneuver around. The booster limiter has a lower noise floor. Some people are finding the 30 or so dB dynamic range was cutting a little bit too much off the bottom. So we gave people an option to say there is no floor, it'll go down to dirt. The problem is that also means it amplifies the noise. It's your call as for people that want the wider range, give it a try. So that's a function of the booster limiter. Gates Air DAX, the digital access cross-connect server, now passed the alarms through to the head end. In the past, the DAX itself wasn't passing alarms through, but there were some large installations that functionality was needed, and that's now available. And the last new feature we talked about is the convex automatic switch assembly can switch between multiple audio paths over a simulcast site. So I can have one path through the T1 or IP network, another RF link path, and this device uses some kind of a logic level input to pick A or B. That lets you have redundancy and use the system in a much more reliable way for those that want to have dual sources. So those are the products that are new in the last few years. With that, I'm going to wrap up and suggest Tom Faulkner has his bachelor's and master's degrees in electrical engineering at the University of California, Davis, specializing in analog, RF, and microwave circuit design. His work experience includes 30 years as an R&D engineer designing RF test equipment for Hewlett-Packard and Agilent Technologies. Tom is a licensed professional engineer in Washington, Idaho, and Montana, and has been working for industrial communications since 2009 as a senior systems engineer. Tom has a success story to share about a TAPE QS2 system that Industry recently installed, and I believe this was the first simulcast system using MIMO-MAX for the microwave. Please welcome Tom.
Oh, yeah. That would be bad. Okay. Ed, how do we get him to actually move? And change slides? The up and down arrows are not working right now. Oh, they are? Okay. They don't look like this display. Okay, so I can do this. Yeah, they were working. Well, as Ed is attempting to do that, Valley County is the northernmost county in Idaho. It borders
shares an international border with Canada. And the county is actually a very small rural county. Population is only about 10,800 people. And so your fire and your emergency medical service is all volunteer. And so it's imperative that when you have a call out, that you can mobilize your forces very quickly. And their repeater system, before they put in the simulcast, was such that they had big coverage errors, and they wouldn't necessarily get the pages out to either the fire or the EMS personnel. As Ed argued for this. So, originally with 2 repeaters up on Dawson Ridge, which will become the central site for the simulcast system. And we basically went in and redesigned or designed them a system such that we could basically fix all of the coverage holes. Good. Leave it on the... Okay. And where's your pointer here? Okay, so what became the central site of the system, also the head-end site, so the monitor receiver, the QS2 circuitry and so on are all up on Dawson Ridge. Dawson has actually got good coverage up the Kootenai River Valley and down along the Highway 2 corridor into Montana. Unfortunately, Dawson did not cover into the city of Bonners Ferry well, which is the main city for the county, and it did not cover the south end of the county. And essentially nobody had coverage up into the very northeastern part of the county, which is where Highway 95 actually crosses into Canada. And so we were called in to design them a system such that we could fix the coverage problems. And so we ended up putting in a system that had 2 channels, one for EMS, one for fire, and it was done at 3 sites. So we have 3 simulcast sites, 2 channels each, and 1 sloppy cast site up in Copper Creek, which is actually a solar-powered site, and so its primary goal was to keep it very low power. The site's actually owned by the Bonner County Television Translator Association, and like I say, it runs off of solar wind with a backup of propane. So, and if you look at these are the actual antenna patterns that we actually used for the system. And so if you look here at the city tower actually gave us coverage into the city of Bonners Ferry, where before we started this, the coverage was so bad that if you took your pager or handheld into the grocery store, you couldn't hear pages. This link here, the backbone of this, was the first time MicroMax was used anywhere in the world for being used in a Simulcast 2 paid system. The link down to Fall Creek, which is in the southern part of the county, Fall Creek Fire Station, brand new fire station, is actually an 11 gigahertz exalt link, and we're using the exalt link without having to put in Simulcast 3 modules into the Gates Air interplex boxes, and so we've saved a hellacious amount of cost doing that. Okay, let's see if we go to the next slide. So this is one of our typical sites. We're using 2 of the Tate 8100 base stations. Each of the base stations has got its own RSU, and the RSUs each have one of the GPS 1 pulse per second time bases in them. And the RSUs are tied together so that if you lose one of the GPS time bases, you have the other. Now, I learned something in designing this system, something you don't do. Originally, the GPS time bases in the RSUs and the master secure sync oscillator all came off of a single distribution amplifier, and we had one GPS antenna. This was actually a very bad idea, because what we lost when we did this was spatial diversity between the RSUs. So we actually had to go back into the sites and add one more GPS antenna at essentially the opposite end of the building to get spatial diversity. So if one of these RSU receivers got blocked from the satellites, we still had the other one going. In each one of the sites, we're actually using multi-couplers for the receive antennas and combiners for the transmit. Now, in this site, right now it's 2-channel, but the sites are all designed such that they can be expanded from 2-channel to 4-channel very easily. And the multi-couplers and the combiners are actually designed to do that as well. Coming through the backhaul link, whether it be coming through as MIMOMAX or coming through as an 11 gigahertz link, we've got the Ethernet coming into a switch and then going to the base stations, the power supplies, and the master sync oscillator, at least for this site. The other sites actually have more that it feeds into. And then the MIMOMAX is running essentially full-time in both directions and carrying the 4-wire audio out of the RSUs back to the central site of the Dawson. Up at Dawson, we've got 4 sites. Well, we've also got 4 ways that we handle our audio. Up at Dawson, their RSUs and receivers feed directly into the QS2 shelves. For City Tower, it's coming through 4-wire audio on MIMOMAX, and for Fall Creek, it's coming through 4-wire audio that is through an 11 gigahertz link. From the Copper Creek site, we have E&M 4-wire audio. This Copper Creek, we wanted to run low power. And so there's an option for MIMOMAX that allows you to take and basically it's transmit on demand. And so it goes from about 75 watts when it's running both transmit and receive down to about 14 watts or so when it's in receive only. And so for a solar powered site, you basically make it so you can save as much power as you can. So the Copper Creek site is actually very simple. Looks very much like kind of a standard repeater, where it's actually just using a duplexer and a tape base station. The tape base station is the only thing on the Ethernet, and it's getting its audio, again, through an E&M card in the tape to control the MIMOMAX where it's transmit and receive. Now, this is a sloppy cast site. And being a sloppy cast site, one, you want to have the power absolutely as low as you can and still get the job done, because you don't want simulcast interference with the rest of the system. The other thing is you want to direct those VHF signals where you want them and not to get into the rest of the signal. So we're actually using a 2-bay folded dipole with a reflector on the back end of it to try and keep the signals from going backwards down the river valley and basically into the rest of the system and causing simulcast interference. Yeah, I'm not sweat. Boy, this is just being fun.
I think you got to point it at the PC, not at the screen.
Well, basically I'm trying to push the button to move this thing, and it doesn't want to move. Can I do it that way? Good. I can do it from the screen. It's got a touch screen on here. I win. Okay, so one of the main reasons you want to use MIMOMAX, if you use MIMOMAX, is to try and get your costs down. Okay, so comparing everything it took to do MIMOMAX versus everything it took to do the Exalt link, there's about 25% cheaper. And you go, 25%, that's not so much a big deal. Until, oh, that's interesting. He does have a touch screen.
You touch something.
Yeah, I did. Okay, if I can do that, then maybe I can do this. Okay, I've got it on this screen. Oh, this is great fun. Now, how do I get the display up there? Anyway,
Windows 8.1 is brand new, sorry.
so's mine. I got it on one of mine. In the ass, I hate it without one. Anyway, basically, you got the cost difference. It turns out with MimioMax, you got a limit of 4 channels. Okay, you can get 4 audio channels down the link because MimioMax is transmitting over a 25 kilohertz wide channel at 900 megahertz. And so if you're building a system that's any bigger than that, then you really want to go to real-life microwave links rather than try and use MimioMax. Another thing that we found with the MimioMax was that the temperature range, at least for Boundary County, Idaho, which can get really cold in the winter, was not wide enough. And so we had to keep the MimioMax inside the shelters, and then run half-inch helix up to the antennas. So that added to some cost. We wanted to have the MimioMax licensed at both ends. The license at both ends at 900 megahertz means it's a 9 megahertz wide spacing between the transmit and receive. And so to do that, you had to use an external duplexer on the system to get that kind of, or that narrow channel spacing. Now, it does have less gain antennas than our microwave links, and actually, in some respects, that's a feature, because the beam width on a MimioMax 16 dBi antenna is about 20 degrees, and so it's a whole lot less sensitive to power movement and to aiming errors as compared to the 2-degree beam width on my microwave links. Okay, looks like we're back on the air. Okay, so let me go to the next one. Looking at 11 gigahertz links, it turns out that the Exalt Explorers will run a native TDM for their T1 connections, as well as a native Ethernet. They're one of the few links that actually has no vocoding. It's native TDM, and it's got close enough time delay jitter, small enough jitter, that you can actually run it without having to have the Simulcast 3 cards in it. And that's provided that you are using it as like a star configuration. You're not using it as a redundant loop where it's going to change direction and change the timing, or you're not using it as an Ethernet express kind of thing and dealing with the time variability of Ethernet. Now, on an 11 gigahertz link, or let's just look at one T1 line. My link's actually can handle 4. One T1 line can be broken into 24 audio channels that are 64 kilobit per second. And with my links, at least, in addition to the 4 T1 lines, we also had 87 megabits of Ethernet, which is more than we'll ever use. The temperature range is such that we could use the outdoor units directly on the backs of the microwave. And so what we were running off the towers then was essentially a gel-filled, armored Cat5e cable for both the Ethernet, the power over Ethernet, and the T1 lines. So, we talked about staging in all kinds of things today. Staging is amazing because we actually found a couple of intermittent connections finding it here where you're walking 10 feet rather than driving 20 miles is a whole lot easier. And so we not only stage the racks, but we actually staged the microwave links as well, because I hadn't used exhaust links before, and it was kind of a risk to know that, okay, are they really going to be stable enough without the Simulcast 3 cards in the Interplex equipment? So, we actually turned them as low as they would go, so we were putting out 1 milliwatt of power, bouncing it off the ceiling, and we were getting enough scattering off the light fixtures that we managed to maintain actually a fairly decent link. Now we could actually measure timing and that sort of thing. So that was actually staged in the shop as well before they were able to deploy. Okay. These are the 9-foot racks that are up at Dawson Ridge, the head inside. And probably more important than what's here, it's what's not here. And so, if you look in here, you'll see these darker blue labels. And the darker blue labels are pointing to places where you could put in the extra 2 base stations and the extra 2 sets of QS2 shells and motors to change this from a 2-channel system up to a 4-channel system. The multi-couplers and the combiners are built the same way, so they can be expanded up to 4 channels. And this thing is also set up so that there's room for another set of Mimamax, so that we can easily expand it also 5 sides. So, at Fall Creek is actually where the system meets the internet. And so the monitoring computer is at Fall Creek. To expand the Fall Creek site to 4 channels, you put in a second rack that's got 2 more sets of combiner and multi-coupler, as well as 2 more tape base stations. The city tower looks extremely like Fall Creek, except rather than a microwave link, it has got a Mimamax link. And we didn't ask for the unheated cargo container. They were actually supposed to build us a nice insulated shelter. But this is what they delivered. And they heated and air conditioned it. And I was actually up at the site last week, and the heating and air conditioning unit is sitting at about a 45-degree angle on the side of the building. And so hopefully it will be installed before summer, because it was 60 degrees when we were up there, and the heat was radiating off of that wall enough that you could feel it on your face. And so in the summertime, if they don't get the building insulated and so on, and the air conditioning in, it's going to cook. Up at Copper Creek, the site is actually very simple. It looks essentially like a repeater, and then it uses the Mimamax to basically connect into the system. Up at Dawson Ridge, which is our central site, we're using 4-bay antennas actually for the receivers on all of the Simulcast sites. Our crew will probably never forgive me for having to put that monster on top of that tower, because they couldn't get a crane in there. And then about 20 feet below that is the 2-bay bidirectional antenna that is for our transmitter. Then coming down the tower, we've got the links for the Mimamax, and then the 11 gigahertz link to Fall Creek, and at the very bottom is the monitor receiver for looking over the system. We learned something at Fall Creek, and that's that you don't put a microwave dish at the top of a tower that doesn't have strong dying. We didn't put the tower in, it was done for us. And one of our tower crew was up at the top, and he swung his hips, and the whole tower moves about 5 to 10 degrees. And so in the wind, you can, before we went through and re-guided, the microwave dishes move outside of that 2-degree beam width, such that you could get your microwave so it was no longer making a link. That actually happened twice this winter, before things were changed over. City Tower was a tower that is self-supporting, super strong, and so on. The only difference that you have on City Tower is we actually have got a 4-bay transmit antenna, because we wanted City Tower to basically have capture effect all around that city to make sure that we didn't get simulcast interference from either Dawson or Fall Creek in the city area. And so we were basically pushing as much power as we could put out in the city. And then up at Copper Creek, there is that directional antenna to basically put the signals where we wanted it so that it didn't get into the rest of the system. So, the things we did well. One, we planned the system such that it could be easily expanded. We put in remote access to a monitor computer. And so it's actually very easy to go and look at the system remotely. You can actually change stuff when you have to remotely, and more important, you can actually train and look at the error logs on the tape stuff remotely, which is very nice. And then the other thing that we did really well is we did block diagrams and documentation and pin-out diagrams and so on for everything. And Ed's got my phone number, and my laptop's going to be basically with him, so that if anybody actually wants to see documentation and so on later, come to Ed's booth. Ed can page me through my cell phone, and I'm more than happy to show people how we actually put the system together. Things we didn't do quite so well, or things that we learned. One is we learned that the Raytheon voters vote from left to right. And so if you want to favor a particular site, in our case it was City Tower, you want to make sure that that's actually in the leftmost slot of that voter. We learned that you don't put up RSUs without having them have their own individual GPS antennas. So we actually went back and added GPS antennas to all 3 sites, so that we could get the spatial diversity we needed to make sure we didn't get GPR link or get GPS timing errors. We learned that you don't put microwave dishes on top of tall towers, tall guide towers, unless you have a star-type guiding system to stabilize them, because the wind will actually tend to try and twist them. And then we're hoping that the city will come through and actually insulate the City Tower site so that, like I say, it doesn't cook in the sun. So that was another thing that we actually begged them not to do, but that's what we got. From a results standpoint, they went basically from 2 individual repeaters up on Dawson that they were having coverage problems. They now have a 3-location simulcast system, each with 2 channels and 1 sloppy cast that is up into where the Canadian border is. They now have basically got handheld coverage at the Canadian border where they were having problems getting into the system with a mobile. And so they're amazed with that. They can now walk into a grocery store in Bonners Ferry and shop in the back of the store and still hear fire pages. And actually go into the ambulance barn inside an ambulance and actually get into the system. Down in the southern part of the county, the fire chief that actually put up the grants to put this whole system together can talk on a handheld rather than walking out into the middle of the driveway for the fire engines, so there's far enough from the building to get into Dawson. And so they're basically elated with their system. And so it's actually a very cool success story. One last quick thing here. Because this is a sloppy cast site, okay, there is a couple of little regions where you have simulcast distortion where it actually makes it, okay? And it's coming off of Dawson and Copper Creek together, and where they get to be about the same signal level in this part of the highway here between the mountains, and then this part of the dirt road actually that's just south of Copper Creek site, that's where we have the simulcast distortion. To keep it from getting farther down though, because when we did the initial testing, he was running at about 20 watts rather than 5. And it was actually getting down into this area here, which is part of the simulcast system, and that was not a good thing. So we remotely, basically, through the Ethernet links, reprogrammed the base station for minimal power, and the problem went away. So that remote access is actually really cool. Anyway, questions?
One question? No, here. I was confused. I'm not having the same experience that you did with the first, thou shalt not do this, because it causes challenges with respect to the voter module in the first slot. Can you tell us what your challenges we received because of that?
Basically, when we had it in the, when City Tower was in the second slot, Dawson was in the first. It would vote to Dawson first, and then a couple of seconds later, we do a switchover. And since the dispatch is actually running an over-the-air link, it would actually generate essentially a change in the audio quality as it shifted over after about 2 seconds, which they really didn't like. And so putting City Tower into that first slot made it such that you didn't get that changeover glitch 2 seconds after the dispatcher hit top. You're going to get the switchover, okay? And that switchover, depending upon how many dB it switches over, it will make a glitch. But no matter what, it will make a glitch. And so if you wanted to prefer a site,
You actually saw the leftmost card preferred.
the leftmost card in the Raytheon board is preferred. Because it's the first thing it'll vote to. It votes literally from left to right.
Yeah, but it votes every 50 milliseconds or something, right? Hey. Okay, so what you were seeing was, as it would jump off that first card to the next card, you saw a change in the audio.
Audio quality.
Quality.
Yeah, it was audio quality that we were seeing.
Thank you, Tom. As a quick reminder, all the presentations will be available online, and you'll also be getting hard copies. So if you couldn't quite read all detail on the slides, they will be available too shortly. Our final speaker is Tom Eccles. Tom has more than 40 years in the design and implementation of radio systems, ranging from broadcast facilities to public safety and transit voice and data systems. He joined the firm of Hatfield and Dawson Consulting Engineers in 1978 and became a partner in 1982. Tom has successfully managed a wide range of radio projects. He's registered as a professional engineer in the states of Washington, Colorado, and Hawaii. Good thinking. Hawaii is a good choice. Tom, Steve Kometz, and Tom Brinkerotter have done some P25 testing. They did a full presentation of this as part of IWCE yesterday, so this is an abbreviated version just to give you a sense of what was available in the full presentation, should you be so interested, but it's a P25 coverage testing. Please welcome Tom.
I'm going to go fairly quickly here because I know we're running short of time. This is, as Ed mentioned, this is a shorter version of a longer presentation in which there's more detail about the equipment used and test setup than there is in this one. So if you're interested in any of that, you can find that on the NBC website after the show. You could also talk to Tom Brinkerotter later about how that all works. came about because we were working on the implementation of a CAD-ADL transit data system for Yosemite National Park for buses and for traffic monitoring and important roadside signs. And what the existing system at Yosemite is a VHF, multi-site VHF system with standalone repeaters and no interconnect system whatsoever. So it's just the users of that system have to switch channels whenever they move from one coverage area, one site to another. And that really was not a very workable system for implementing CAD-ADL for the buses. They are implementing a microwave interconnect to all those sites over the next 2 years, and so we knew that eventually there'd be an interconnect system available when we could implement a Simulcast system. The issue we had was that the CAD-ADL system needs to be able to send a poll for data or request for data from the buses out without having to know. With a standalone set of standalone repeaters, it didn't have any way of knowing which repeater site to key out where a particular bus was. And we looked at various alternatives to how to solve that problem, and the best alternative we came up with was a simulcast system, so that any poll that goes out of the system will reach all the vehicles that are out there. Also, modern CAD-ADL systems really require some form of IP interface and not an analog system. So we really were moving in the direction of D25. We looked at the option of a trunk system, and it just simply wasn't viable. There were frequencies available, and it was way too expensive compared to just do a simulcast. So I'll actually not spend much time on this one because Joe talked about this a little bit, except to say that these are kind of the assumptions we use when we design simulcast systems. Non-capturable lab areas, 15 to 20 dB for a digital system, C4 or LSM. And then delay spread, it's pretty similar for analog and LSM modulation, and it's about half, you can tolerate about half as much delay spread for C4 FM and D25. The two sites, actually we did 2 different pairs of sites, but the sites we were testing in the Yosemite Valley had significant non-capture overlap areas where there were large portions of the valley where the signal levels between the 2 sites were within 10 dB and sometimes identical. And so we knew that could be an issue. And fortunately, the Yosemite Valley is not very long, it's only about 8 miles long, and the distance between the 2 sites was, I think, 6 miles. I got that in a later slide. So the worst case delay spread was probably on the order of about 40 microseconds, maybe. And actually, in most areas of the valley, it was better than that. So longer delayed echoes than that would certainly cause problems for C4 FM. And eventually, even depending on the amount of delay, would also cause problems for LSM. We didn't see that in the test that we did. This is a picture of the Yosemite Valley looking from the tunnel view viewpoint down east into the valley. And as you can see, it is just an ideal environment for lots of mobile path. The sites are elevated sites at the top, or even the site in the valley, illuminates all those vertical walls, and you just have enormous amounts of reflected signals all over the place. One of the reasons I decided we needed to do some testing was this is a radial running from the Sentinel Dome site down through the valley and up the other side. And Sentinel Dome's up here. This area down here is we ran coverage maps, coverage predictions with a standard coverage model that didn't have any way of doing any reflections or ray tracing. And this area down here showed up as being very bad in shadow, which it is in that site up there. And we had predictions in the -90, -100, -105 dB range. When we went out and actually made some spot measurements in here, the signal levels were more like -7. So the reflections off of this wall over here back into the valley on this side were the main source of the signal in that area. The whole valley is pretty much like that, but vertical rock walls being traveling over the Yosemite Valley. The 2 sites, we tested 3 sites, Turtleback Dome, at the west end of the valley, Sentinel Dome, both high sites, Sentinel Dome at east end, and we also tested the site in the valley itself, Yosemite Village. So we did 2 pairs. Turtleback Dome was common to all the tests because it provides So we did a combination of Yosemite Village and Turtleback and Sentinel Dome and Turtleback. And we tested both C4FM and LSM modulation. Here's where I use an elevator. We did some initial testing just to test P25 from a single site, or a couple different single sites. Because I was a little worried that P25 might have issues just because of the severe multipath. And so we did those tests initially. When we did those, we also got measurements as we were doing the drive testing, and that's what this video shows. Okay. Now we have to go to the screen. Yeah. Yeah. Keep showing this. It looks like it's not going to run on this little computer, so if you're interested in looking at it, it's a really interesting video of what really severe multipath in this environment looks like as we're making a measurement of Eurospan oil and spectrum analyzer. So it's a time domain measurement of essentially mean signal power level versus location versus time in this case, but actually time corresponds to location. And so we had 2-second screenshots and we strung them all together as a video, and you can see the worst case nulls in the multipath were in excess of 40 dB compared to the mean signal level. So it was really severe multipath as we expected. So we measured RSSI, bit error rate, and modulation fidelity from the 2 pairs of sites. And we tested both C4FM and LSM. We used a 3 dB gain Omni antennas at the sites. We also, at Turtleback Dome, had a 7 dB gain corner reflector directional antenna, which we had up there in case we ran into overlap issues in the middle of the valley where the signal levels were very comparable from the 2 sites. We could reduce the signal level from Turtleback in that area by using a directional antenna. We did testing with both the Omni and directional, and it turned out that we didn't actually need the directional antenna. 32 watts ERP for the Omnis and about 83 watts for the directional. And one thing here is, in a situation like this, low power is better than high power. So 32 watts did just fine, providing very good coverage, and you wouldn't want to run any more power than that because you would simply increase the strength of the electrical mix. This is the test setup, and Ritsu vector signal generator tied to a Trimble GPS oscillator, and then we had a linear amplifier because we were testing LSM and we needed a linear amplifier. A dual isolator band cascade the transmission lines up the antennas. So both sites were set up identically, and there was a process by which we had 6-meter radio to communicate back and forth, and we did a 3-2-1 countdown so that a person at each site pushed a button on the generators, and they started in sync at the next one GPS pulse from the Trimble oscillators. So that worked. They synced up very well, and what we had in the Well, this is the great scenic shot of what we had in mapping antennas and measurement antennas mounted on the aluminum plate in the bed of the truck, Tom Brinkhauer's truck, and then it's the speaker antenna for voice and half dome in the background. I guess I'll let that other slide out. There's what we had in the vehicle were 2 S412B LMR masters. One was used to do the bit error rate measurements, and the other was used to we used the other one to watch the eye diagram for the signal we were testing. So this is what we assumed for bit error rate and signal quality and the maps for color coded display. 2% bit error rate corresponds to B8P3.4 or 4P25 at this point. So this is what the measurement maps look like. On any one of these measurement points, from the LMR master, you can click on the measurement point and it expands and shows all the measurement data for that point. So it's pretty handy. The red right here in the middle is the Pomona tunnel. Actually, the VHF coverage extended at least a couple hundred feet into the tunnel on each end, so that's tunnel slightly longer than what showed in the measurements there. And then, so this is the Yosemite Valley here. This is the road out to El Hotel. And this is Highway 41 to Fisher Point Road up towards San Antonio. And this is, let's see, this is C4FM with on the antenna terabyte. So, this is the same measurement. Actually, I'm just showing these two as a comparison between what C4FM looks like, where you can see that there are some issues here that were related a lot to multipath. And down in here, there were also single strength issues. The power society was fairly low. The C4FM, there were some issues with, this is the same test with OSM, with those same two sites. As you can see, there's a significant improvement in bit error rate performance along the Glacier Point Road. So the LSM really does make quite a bit of difference in areas where the C4FM signal is marginal in terms of bit error rate. This is just a comparison of the single site measurements we made on the Central Dome with C4FM, and that was actually worse than the simulcast measurements with C4FM. So the simulcasting two sites did provide better coverage along this area. And this is the simulcast version down here with LSM, which, with the exception of this area down here, which is shadowed on both sites, it provides that configuration of the two sites provides very good coverage. So the conclusion we came to was that P25 simulcast operation, phase 1 simulcast operation would work well. We're recommending using LSM because it makes a big difference and provides more coverage. So the P25 simulcast operation works well in environments with a combination of high levels of multipath and significant non-capture overlap. As long as the delay spread values are low enough, and in this case they were. With longer delay spread values, you get a longer valley where there's a possible reflection where you can get 70, 80 microsecond delay spread. You may have serious issues. Again, we figured probably that the delay spread value is worst case in areas that are measured on a product of order 30 to 35 microseconds. So the C4FM was fine with that, and LSM was also fine. The best overall coverage was provided with the two sites, Turtleback Dome and Simulcast antennas. And we found that we did not need a directional antenna at Turtleback in order to minimize the overlap area. But what's not in this presentation, but is in the longer presentation, is a slide or two that shows how much the directional antenna reduced the signal coverage from Turtleback into the Yosemite Valley. It was significantly increased it by 30 or 40 dB. So if we had an overlap problem, then that would solve it. LSM provides a significant improvement for both bit error rate modulation fidelity over C4FM in any areas where C4FM is marginal in bit error rate performance. And this test technology worked very well. We were really lucky. The weather was good. We didn't have any issues with access to sites. None of the equipment failed while we were testing. Everything went well. So it was some kind of the ideal test circumstance, and we lucked out. But this methodology, it allows you to do set up what looks exactly like a simulcast system without having any system infrastructure. We had no interconnect system. All we did was have the tower crews, the Yosemite mountain antennas on the towers and transmission lines, and we assembled Steve and Tom schlepped all that equipment into the buildings and put it all together, and it provides a very good way of doing this kind of testing to verify that some site configuration that you're looking at for simulcast will actually work for P25. Just some acknowledgement is here, and Ritsu provided both Tom Brinkhart's time and the test equipment for this, and then David Engelstad and David Thorpe